Now, this stuff gets tricky when you do low power, and to talk about low power, I want to invite Scott Hansen, founder and CTO of Ambiq, up on the stage.
Thank you.
Power's crazy in these devices. So the conversations we've had with customers on just how much we need to squeeze out of these devices when they're on all the time,
Yep.
monitoring humans, is really incredible. And you've done super smart things with Ambiq in this space. Tell us what the reality is around AI, which is consuming some data centers and power plants. Microsoft recently tried to buy a nuclear power plant. Said it. Power plants worth of energy to run AI, and now we have to do it on a tiny battery.
Yeah. No, it's a big problem. You're in the cloud, you've got gigahertz, you've got gigabytes. Most importantly, you have kilowatts, right? At the edge, we have none of that. We are incredibly constrained, and actually, let me quantify it for you. So I did some math before I came here. Your typical wearable customer might have a 50 milliamp hour battery. Imagine that you're building a wearable, you want that to last for 7 days. Do the math, you'll turn out, you got to be at about 1.1 milliwatt average power, which to me sounds like a tremendous amount of power, by the way. Okay, it sounds like a lot. Many of you are looking at that thinking, wow, it's tiny. But actually, that's not what we have available for inference, right? That's what you've got available for UI, for graphics, for sensors, for security, for communications. And then there's a little sliver left over at the end for inference, right? So actually, let's say we give ourselves 10% of that power budget for our wearable device here. You're looking at 100 microwatts for inference, right? That's a difficult problem, and actually that's the problem that I founded Ambiq to solve.
So how does that work, right? I mean, I came from ARM, or we're working with low power all the time. Why isn't Cortex-M on standard processes good enough, right?
Yeah. Well, we'll let Paul talk later about why the Cortex-M is a wonderful solution for everywhere. But what Ambiq does uniquely is, first of all, we build the world's most energy efficient chips. We've shipped more than 250 million of them. They're ARM-based devices with little GPUs and memories and all sorts of other things. And we are between 3 and 10 times more energy efficient than the competition through use of a technology that we call sub-threshold or near-threshold operation. And we've got a marketing version of that called sub-threshold power-optimized technology, SPOT. I'm not going to get into, that's a whole other discussion we can have another day. I'm not going to get into the specifics, but the basics are we're running at a much lower voltage than you typically operate transistors at. Energy is voltage squared, so as we drop that voltage, we're getting huge energy savings. And so what does that mean for all these developers out here? Maybe it means longer battery life, but frankly, my guess is most of these attendees here are not thinking about that. They're thinking about how can I bring AI where there was none before? And 3 to 10 times energy advantage means 3 to 10 times bigger AI models. It means I can put 3 to 10 times more compute in the same energy envelope, and that's a flexibility that's pretty incredible.
Right, so lower power doesn't necessarily mean less compute. It might mean more compute per watt, right?
Yeah.
So we can do more AI.
Exactly.
This is exciting, and we started working together on the Apollo 510, which brings in acceleration. So what do you see acceleration for AI enabling at this kind of low power threshold of what you're working on with customers?
Yeah, I mean, first of all, there is a place for that. I think the Apollo 5 is based on the Cortex-M55. You have a helium vector unit. You can run 8 max per cycle, and that's luxurious for most of our customers, right? I'm going to say that probably 75% of the applications that we see at customers don't need an NPU, maybe don't even need that vector accelerator. Actually, you can do a lot on a very small amount of compute. So actually, it's worth bringing up a couple of our customers who are doing this today. So we today are serving many different wearables customers. We're talking about wearables right now. If you were to go to Best Buy and walk down the aisles of there, you'd see our chip in devices like Garmin and Fitbit, Google, Huawei, Xiaomi, all sorts of companies I can't name. But what we're seeing is a migration toward more medical-oriented devices, right? So these are devices that look like wearables, right? They might look literally like this thing I'm wearing, but they're for a clinical setting, right? They're sitting there on a patient in a hospital or a patient who's gone home. And one of the customers that I'll bring up is a company called BioStrap. So really cool company that has built a device that looks very much like the wearables that you see everywhere else. What they've done is they've taken our Apollo 4 based device and built a bunch of neural networks on top of that. And they've done so for all sorts of what I call small AI reasons, right? So what I mean by that is, in small AI, you're taking a traditional algorithm, traditional filter, whatever, and you're replacing it with a neural network. You're doing the same thing you did before, you're just doing it better with higher accuracy, right? And this is actually the vast majority of what we're seeing at customers is exactly this, right? So back to your comment on LLMs and all that stuff, this is the kind of thing people are building. And in BioStrap's case, they are using models to detect the onset of sleep, to detect when sleep is finished, for heart arrhythmia detection. These are all really exciting things that they could do before without a neural network, but they're doing it much better now. What's cool is they're using Apollo 4. This is a maximum 200 megahertz processor with a couple megabytes of memory and a handful of other resources. So this is not, there's no NPU, there's no need for an NPU, right? I mean, in this particular use case, there's no need for expensive memories and all that. This is a very well optimized set of models that fit on a small processor. Another customer that I'll bring up, this is not a wearable, but I like to think of this like a Fitbit for industrial machine equipment. You already talked about anomaly detection earlier, but we have a customer called Shoreline AI that has a edge-to-cloud solution where they're taking little battery-powered devices that they put on industrial machines, monitor the health, look at vibration signature, sound signature, and then flag when there's a problem that's imminent. And again, what's exciting here is they're actually using an even smaller processor. They're using the Apollo 3 generation, which was launched back in 2018. This is a Cortex M4. It's got, again, 1 or 2 megabytes of memory. It's got no particular acceleration, but it is incredibly energy efficient, right? So you combine all that together, you add in a good software stack, and we've got a case where Edge AI is suddenly feasible. You don't need to worry about the gigabytes and the gigahertz and the kilowatts. Suddenly we can build right-size 100 microwatt models that are suitable for the edge.
So for me, the holy grail feels like, how do we squeeze more algorithm into the silicon at an MCU level?
Yeah, absolutely.
Yeah.
Absolutely.
Awesome. So we've got a demo of the Apollo 5 with Edge Impulse running out there. It's very cool.
Yeah.
I want everybody to go check it out. And please, if you want to talk about low power, come find Scott during Imagine today and nerd out.
Awesome. Thank you.
Scott.